This is lecture 5 of unit 11, and in this lecture we'll talk about gas law calculations. Recall that we talked about the 4 gas laws, Boyle's, Charles, Avogadro's, and Gay-Lussac's law, that related pressure, volume, temperature, and moles. And now we're going to apply some math to it, do some calculations, and we will do it with something called the ratio method. You'll see what this is as we go along. So the first example, example 3, let's take a look at it logically, what it's asking. And we're saying that indoors, where the temperature is 20 degrees Celsius, a balloon has a volume of 4 liters. What will its volume be if it is taken outside where the temperature is 10 degrees Celsius? So the idea here is we are going from 20 degrees Celsius to 10 degrees Celsius. And our volume goes from 4 liters to what? That's kind of the idea. Now, the law here is between temperature and volume. So we have temperature and we have volume. And we know that temperature and volume are directly related, which means as temperature goes up, volume goes up, or as temperature goes down, volume goes down. In this case, we have temperature going down from 20 to 10 by what looks like half. So we would expect volume to go down from 4 down to 2 liters. Now, this is the correct logic to use. However, if you think about this, will a balloon, say if you blow up a balloon, which is 4 liters, a pretty good sized balloon, and this is kind of a regular temperature inside, kind of a cool temperature inside, and this is the regular temperature maybe on a cool spring day, will the balloon get half as small? Will this happen? And the answer is it won't get half as small. It'll get a little smaller. Maybe it'll go down to 3.8 liters. I mean, it'll get smaller, but it will not get half as small. And the reason why I show you this example is to demonstrate that we have to use Kelvin for our gas law calculations. You cannot use temperature, you can't unless use Celsius as temperature. You have to use Kelvin. And remember that Kelvin is, you have to add 273. So it's degrees Celsius plus 273 if you want to get to Kelvin. So here, plus 273 would give you 293 degrees Celsius. And this is 283 degrees Celsius. So now, looking at these two numbers, you could see that the temperature did go down, but it didn't go down by half. It went down by a small fraction. So our volume won't go down to 2. Our volume maybe will go down to 3.8 or something. And we'll be able to calculate this in a little bit. So hopefully this makes sense. You have to use Kelvin for all calculations. You can't use Celsius because it is not an absolute scale. So let's go ahead and do an exact problem involving this sort of thing in number 4. So number 4 has Kelvin for us. At a temperature of 273 Kelvin, the pressure of a gas is 2 atmospheres. What will be the pressure at 415 Kelvin? So here we see temperature going up, and our pressure should also go up proportionally. Let's do this using the ratio method. And the way we will work with the ratio method is we will put down our 2 variables. So here our variables are pressure and temperature. So I'll have T1 and T2, should be a 1. Good enough. And we'll have P1 and P2. Fill these in. Essentially we're keeping track of our data. Our first temperature is 273 Kelvin, so we'll put 273 Kelvin. Our second temperature is 415 Kelvin. That's what we'll put here. Our first pressure then is 2 atmospheres, 2.0 atm. Make sure you include the units. And our second pressure is the one we want to try to find out. We don't know the second pressure. The way to use the ratio method is we will begin with the pressure, the one we're solving for. We'll begin with the first pressure, 2.0 atm. And then we will multiply this by a ratio. And this is why we call it the ratio method. And this kind of looks like what we do when we convert, but it is not. what we will do is we will multiply this by the ratio of the temperatures, because the temperatures are going up. From our Gay-Lussac's law, we know the pressure must go up. So this pressure must be increased. So these two numbers will go into the ratio to make sure this number is increased when it is multiplied. So if I want my atmospheres to go up, I would put the big number on top, 415 on top, the smaller number on the bottom, 273. This ensures that I pull up my pressure, because my temperature going up should cause my pressure to go up. So if you do this calculation, if you do 2.0 times 415 divided by 273, you will get yourself 3.0. In this case, the unit would still be ATM, so put 3.0 ATM. In this case, if you take a look here, this is Kelvin, Kelvin, so these cancel out, but the ATM does not cancel out. So 3 atmospheres would be the new pressure. So take a look at it. This is we're going to do another example. The reason we call this the ratio method is because you're simply multiplying what needs to change by the ratio of the other, you could say, characteristic or parameter. That would be the word. Let's try one more. Try the next one using the ratio method. So in this case, we have a balloon filled with helium, has a volume of 235 milliliters at 765 torr. What volume will it have at 148 torr? So here we have two variables that we're working with. Milliliters is volume, and torr is pressure. Let's set up our data as V1, V2, and P1, P2. So our V1 is 235 milliliters. Our V2 is actually what we're asked for. What volume will it have? So this is our question mark. Our P1 is actually 765 torr. Our P2 is 148 torr. And what we'll see is we'll have to solve for volume. So go ahead and put volume down to 35 milliliters. This is what has to get changed, and it will get changed by the pressures. So this pressure ratio will go in here. The question is, which number do we put on top, which on the bottom? Now, whenever pressure decreases, here we have pressure decreasing, we know volume must increase. This is because of Boyle's law. As pressure goes down, volume goes up. It is inversely related. So again, pressure decreases, volume must increase. In order to make this volume increase, we have to put the big number on top. So 765 would go on top, torrs, and 148 torr would go on the bottom. And when you multiply, you should see volume go up. So go ahead and multiply this, 235 times 765 divided by 148 gives us 1,214. Now, because we have 3 sig figs, let's do 1,210 milliliters. So notice what we predicted is that volume would go up. That's because pressure is going down. And volume did go up from 235 to 1,200. And it's always a good idea to double check to make sure what you predict is what actually happened. Okay, so go ahead and try this on your own. This next example problem essentially applies the same idea. Try it on your own. And let's finish up with this example problem. This one actually combines the two concepts into one. The example says a gas has a volume of 175 liters at 18 degrees Celsius and 150 kPa. At what temperature would the gas occupy 1.30 liters at 210 kPa? So here we have volume, here we have pressure, and here we have temperature. So we actually have 3 variables that we'll have to keep track of. So let's go ahead and put these out. We have V1, V2, V2. We have T1, T2, and we'll have P1 and P2. So 2 of these 3 will be changing, and the third one is the one we will predict. Let's fill these in. Our first volume is 1.75. and go ahead and put the units in as liters. Our second volume is actually 1.30, so 1.30 liters. Our first temperature is 18 degrees Celsius, and our second temperature is what we'll find out. So at what temperature? So this is our second, this is our unknown. Our first pressure is 150 kPa. Our second pressure then is 210 kPa. Now before we start this problem, we have to adjust one of these parameters, and that is temperature. Our temperature has to be in Kelvin, and we have to add 273. So 18 plus 273 should give you 291 Kelvin. So actually, this is our temperature, 291 Kelvin. Once we have adjusted that, here's what we need to solve for. We need to solve for temperature. So it is the temperature we'll begin with. You always begin your ratio method with the one you have to solve. So you have 291 Kelvin. In this case, we will multiply by two ratios. Since we have volume affecting the temperature, we have pressure affecting the temperature. So let's do the volume first. Let's put this ratio in here. And the question is, how does volume affect temperature? Well, in this case, volume goes down. When volume goes down, what happens to temperature? Temperature must go down because of Charles' law. So for temperature to go down, I would put the small number on top, 1.30 liters. Put the big number on the bottom, 1.75 liters. Let's take a look at the pressure. What will the pressure do to the temperature? Now the pressure here is actually going up. When pressure goes up, we know temperature must go up. So as pressure increases, temperature will also increase. So since pressure goes up, since pressure goes up, temperature must go up. In order to pull temperature up, we must put the big number on top. So 210 kPa and 150 kPa. Now if we multiply these together, we've got 291, go ahead and do this, 291 multiplied by 130 divided by 175 times 210 divided by 150. The final answer is actually 302, so we'll put it in here, 302 Kelvin, because this is the temperature we're solving for. Here is the final answer. So let's quickly reiterate this as we wrap up. What we did is we said the temperature we must figure out the temperature. So to figure out the temperature, we take a look at what volume does to it, and we take a look at what pressure does to it. Here we see that volume decreases, which will pull temperature down. That's why we put the small number on top. Here we see that pressure increases, that will pull pressure up. We'll put the big number on top. So this ratio here pulls temperature down, this ratio here pulls temperature up. In the end though, the temperature got slightly pulled up because the pressure won. So go ahead and try one of these on your own, and we will practice this in class and we'll apply it to the gas laws.